Hello and welcome to this video. In this video, we will start implementing the transitive closure function. So if you have not watched the previous video in which we discussed the theory of transitive closure, I will strongly recommend to watch the previous video. Once you have watched it, you can continue watching this video. So in this video, we will implement the transclose function, which will give us the transitive closure of a graph. So this will receive two input elements. One is the edges and another is path. And we have two more variables, new prod and adjacent prod. So first we iterate through the edges and we take out the adjacency value of the edge and assign it to path and adjacent prod. So this is basically define our initial edges. Now we iterate from I is equal to 1 to max nodes, where I represents the number of times adjacency matrix has been multiplied with itself to obtain ADJ prod. Okay, so whatever is the length of I, whatever is the value of I, that will be the length of the paths. So maximum path length will be max nodes minus 1, because if there are two nodes, the length of path would be 1. There are 3, then the max length could be 2. So it makes sense that we have max nodes minus 1 path length as the maximum value of the path length. The reason is, suppose you have a linear graph in which all elements are connected one after another, then between the first node and the last node, the path length would be max nodes minus 1. So we send the adjacency prod, edges and new prod to our prod function, which will multiply the matrices. Now remember, the ADJ prod will in the first iteration it will contain the path length of 2, not 2. This will contain the path length of 0 in the beginning, and new prod will contain the new path length which we will get by multiplying these two. So the prod function is simple. What it does is it takes A, B, C, 3 matrices, and it multiplies them. And the initial assumption is that there is no path between, basically, no path between two nodes or vertices. So it multiplies, ORs them, and assigns it to C, where C is new prod. So this, our new prod is populated, and we OR this with the path and assign it to path. So if you remember this algorithm, what we are trying to do is we are trying to compute this guy. Okay, this is the matrix multiplication we are trying to perform. So once we have our new prod, we put it inside path matrix, and once we have our path matrix defined, we copy the new prod to adjacency matrix of multiplied times. So this will finally contain the this will finally contain the multiplied matrix of new product. So if you see the complexity of algorithm, the prod has 3 loops, which is order of n cube, but this prod is already inside a max nodes. So the overall complexity would be O(n) to the power 4, which is quite bad. So there are algorithms to fix this. We will go there in a bit. So eventually what we have after this entire iteration is this product of adjacency. So this ADJ prod will contain all the paths, or rather I should say this. So it will contain ADJ, it will contain ADJ2, it will contain ADJ3, and everything after that. It will contain all those matrices here. Okay. So now we move on to maybe I made a mistake. Now ADJ prod won't contain everything. It will contain the current iteration of that. Okay. So in the beginning, it would be of length 1 or rather 0. And then it will contain of length various lengths from I. Right. So we now move on to Warshall algorithms, which reduces this complexity to order n cube. So let's see what Warshall algorithm is. So what we do is we define a path k ij to be true if and only if there is a path from vertex I to j that does not pass through any vertices higher than k except for I and j. Now if path k ij is true, then path k plus 1 ij must also be true, because k plus 1 will restrict it to k plus 1, but we already have no vertices higher than k, so there can't be any vertex higher than k plus 1. That is why path k, if path k ij is true, then path k plus ij will also be true. However, if path k ij is false, then for path k plus 1 ij to be true, there has to be a path from I to j through k plus 1. Okay, but there should be no path from I to j through nodes 1 to k. This second condition implies that path k I k plus 1 is equal to true, and path k plus 1j is equal to true. So either path k ij is true or this condition is true, then there exists a path k plus 1 ij. That is the entire summary of Warshall algorithms. Once we have this, what we can do is we supply edges and we have path. Okay. What we do is we copy the edges matrix to path matrix. Once we have that, we iterate over the outer two loops, and what we do is if path ik is true, then for these many nodes we copy the odd part of this into path. Okay. So that's the simple algorithm of Warshall, which reduces the transitive closure matrix which we have defined earlier. So with this we come to the end of this video. In the next video we will start trying to do shortest path algorithms and such things, and then we will move on to adjacency list presentation of graph, because adjacency matrix, as you can see, this consumes a lot of memory and a lot of it is unnecessary because there is no path between them. So adjacency matrix is not needed here for this. So we will continue with those things. So stay tuned for next video, and I'll see you in next video. Thanks a lot for watching.